Thank you, Costas, for the introduction again. And today, in the third lecture, I'll just follow up on what I was talking about yesterday in the first two lectures. So just to give you a quick summary, yesterday we saw that when we have a one-dimensional quantum system which has a gap spectrum and has a local Hamiltonian, then you can use matrix product state uh, acronym MPS to represent those kind of ground states of those kind of systems. But suppose I have a 1D quantum Ising spin chain, and I go very close to the criticality, then the MPS methods fail because uh, there's a upper bound on the entanglement I can reproduce, and for critical system that is not good enough, and we have to go to some other method, which was which was discussed, not discussed completely, but yeah, it was mentioned that it is called MERA. Uh, then we move to the real space tensor RG method, which is the Lagrangian approach or the action approach to tensor networks, where you have a partition function or say, for example, exponential of the minus Euclidean action, and you want to approximate that. So sometimes what we do is we use Monte Carlo methods to compute some observable, say, for example, Wilson loop or say magnetization in some spin model and things like that. But you can use tensor RG methods to do the same thing. And then, so today, after giving a little bit of introduction in the first 10 minutes and going over a couple of things which I thought was not clear yesterday, I'll move to again to Google Colab and show you the example of the exact diagonalization for 1D quantum Ising spin chain. So what I'll do is I'll consider a spin chain with some Hamiltonian, which I'll explain. And that Hamiltonian is known as transverse field Ising model. It's a very popular model, also known as TFIM model, transverse field Ising model. And the exact solution for that model was given in the 1970s. And the ground state energy is written in terms of some elliptic functions. So we'll do exact diagonalization, and I'll show you how close do we get to the exact results. And then from that, I'll move to discussing more about the fundamentals of tensor, writing the contraction codes, which we saw yesterday, which I drew diagrams yesterday for, where you have a lot of indices. How do you contract those networks? And that will eventually lead us to this notebook, which will deal with the tensor renormalization group, TRG, or a higher order version of TRG. I'll explain why it is called a higher order version. So higher order version is just higher order HOTRG. So higher order TRG version is useful for higher dimensional system and also more accurate than the TRG methods. So I'll get to that. So I think we'll finish somewhere after the fourth point, or maybe we'll be able to reach the fifth point, basically, starting with some basics, going to ED and then TRG. Okay, so one of the things which I think was not very clear yesterday was there were some questions about the A tensors in the MPS. So I thought, what is the best way to explain that? And I think I should have done it yesterday, but let me do it today. So suppose I have a state like this. This is a state we saw several times yesterday, which is called the GHZ state, right? Now, suppose I give you this state and ask you, what is the matrix product representation of this state? Okay, so for that, we can write down the matrix product representation state. So for example, we need 3 spins, right? Because there's 3 qubits. With something like this, where these are A's, and then you trace over those things, right? Now, how does it really work in practice? Now, note that these indices here are the physical indices. So they can be 0, 1, 0, 1, and 0, 1, right? So now, what we have is, suppose we have a matrix, which is A0 is equal to, and we have A1, which is equal to, right? So the first one is corresponding to the spin up, physical index 0. This one below it is corresponding to the physical index 1, 0 and 1, right? If this was, say, for example, some spin 1 system, then I would have to write 0, 1, and 2, and so on. You get the idea. Local Hilbert space dimension is number of the A at each side. So now, suppose I want to write down, the whole point is to write down the coefficients, right? So as we saw yesterday, you have the bases, which are these. So bases are just like a bit strings, like 0, 0, 0, 0, 1, 0, and so on. But what is important, the coefficients, right? So the matrix product state, which we saw, is going to approximate the 2 to the n coefficient with some small number, right? How do we get the coefficients in this case? So for example, this is a 3-state GHZ model. So if you want to get, say, for example, this term, then you just take a trace of A0, A0, A0. And this will give you 1 over root 2. There's a normalization which I've forgotten, but you can rewrite the normalization. Normalization is just equal to right, because you want to get 1 over square root of 2 factors, you have to multiply some number of them together, and then I think it's 1 over n or 1 over 2n. That normalization is not important. But if you do this, you will find it is 1. And if you do this, you will see that it gives you 1 over square root of 2. So that is why this is a matrix product representation, because when I take 0, 0, and 0, it gives the coefficient of 1 over of 0, 0, 0 term, which is 1 over square root 2. If I do A1, A1, and A1, it gives 1 over square root 2. Now, you can rewrite the matrix product also for a W state, which is more complicated. But I'll leave that as an exercise. It's on Wikipedia. You can check if you're interested. Right? So in this case, you still have 2 physical indices, but you have 3 different matrices, but those matrices might be, you have to find out. You have 3 sites and 2 physical, so you have to find out different A matrices, which will give you the coefficient 1 over square root of 3. So this is what is called a matrix product state representation. Wait, what did happen? Okay, so this is what is known as the matrix MPS representation of GSZ state, right? Okay. Now, what we'll do today is we'll consider, as I said, the transverse field easing model. Right? The transverse field easing model is given by the Hamiltonian. Where Z and X are the Pauli matrices. Right? So there's a ZZ term with some exchange coupling J, and there's a magnetic field term which is transverse because this is Z and this is X, so this is transverse. That is why it's called transverse field easing model. You can study the system at H equal to 0, and then it's just there's no external field. But this model is more interesting because this model has a phase transition at H equal to 1 in units so setting J equal to 1 basically. So we'll set J equal to 1, and in that case, H equal to 1, there's a phase transition, right?
I'm a bit confused. Are you in how many dimensions is this?
This is in 1 dimension. So this just everything is on a line basically.
So what phase transition is?
This is quantum phase transition in transverse field easing model, H equal to 1, in the thermodynamic limit, obviously.
I'm just confused about the statement about no phase transitions in 1 dimension.
Oh, no phase transition in lower dimension? Which statement?
1 dimension.
Sorry?
Wasn't there a statement about no phase transitions in 1 dimension?
That's right. That's for continuous symmetries, not for discrete symmetries.
Oh, I see. Okay.
This is Z2.
Okay.
Yeah. Okay. Yeah, that theorem is called Mermin-Wagner or Coleman-Mermin-Wagner theorem. Yes. So that is that precludes a phase transition of this kind in one quantum or two classical dimensions. But in this case, we have a transition because of this C2 in the thermodynamic limit, and this model was studied by people in the 1970s, and there's a result from this paper which says that the ground state of this Hamiltonian basically is equal to 2 over pi 1 plus h, some elliptic function of second kind with arguments pi over 2 and theta, where theta is nothing but 4h over 1 over h squared. And this was derived using, this was derived using Jordan-Wigner transformation, obviously the standard one, and solving it. So this paper is also has results for magnetization. I'm writing this because when I do exact dilation, I want to see how many spins do I really need to approach this thermodynamic ground state normalized by the number of sites. And we'll see that we need at around 10, 15 spins or something. I cannot go to 15 spins on my laptop or Google Colab, but I'll show you how it approaches this result when we increase the number of spins. So this is the exact result. This is not very strange that there is elliptic function here, because even if you do a two-dimensional classical Ising model, like looking at the Onsager solution, the internal energy of, for example, you can write Z, then you can compute the internal energy like dln by d beta or something. And then even in that case, the internal energy is some sort of elliptic functions. So these elliptic functions are well known in Ising model. Okay, so the goal now is to write a code and do this. Obviously, if I could do n equal to 1000 on my laptop, then there's no need of tensor networks. But as we'll see, we'll eventually run out of steam and won't be able to do like more than 10 in a reasonable time. If you go to bigger computers, maybe you can do 15, 20, but obviously you cannot do a lot. But with tensor networks, you can do like thermodynamic limit pretty quickly. And you can also find out, look at this phase transitions, and people compute correlation functions at this phase transition. Obviously, we know that in a gap theory, the correlation functions decays exponentially, but in a gapless or a critical system, it has a power law behavior. So people have reproduced those kind of power law behavior at h equal to 1, for example, for quantum Ising model and things like that. Using MERA, using MPS, you cannot reproduce the power law, but using MERA, people have done it. So a lot has been known about this, so you can read up if interested. So now what I'll do is I'll just move to Google Colab again, and then try to see if we can, let's see. Okay, so the plan, okay, yeah, so I have to share my screen. Just a second. Yep. So I'll, let's see if I can. Okay, so let me share my screen here. So we open the Google Colab again. I have the same notebook, but probably I'll create a new notebook for day 2. I have to, for example, right now, I don't really need those things to install, so I'll just paste the code. But I wanted to show you about the exact dilation thing. I'll explain it and show you the results. Yeah, there's a couple of checks I was doing, so I'll just. So, okay. So this is the exact dilation for which we are going to do. You can try, if you want to, if you're interested, you have your laptop open and you want to do this with me, just let me know. I'll paste this code in the chat. But I'm not sure how many of you were doing it live yesterday, so I'll just only do that pasting if you request it. So otherwise you can just see it here and I'll explain everything. Okay, so the first thing is we import the usual stuff from the libraries. We need NumPy, we need to plot some things. Okay, so yeah, please paste in the chat. Okay, sounds good. Yeah, I'll paste in the chat in a moment. So let's see. Yep. The message is too long. Please try sending multiple shorter messages. Okay. This is the first short message. And this is the next short message. Okay, so we import things, we just define, you don't need to do this. I don't know why I was doing this, but it's useful. So E is NPI, which is the identity matrix of 2 by 2 size. NPI is identity matrix of 4 by 4. Then I defined sigma X, which is X. Sigma Z is Z. Then I do a canonical product of Z and Z, like np.cron ZZ. And now I could build the Hamiltonian. So when I build the Hamiltonian, for example, here, I build it for the number of sites, value of magnetic field, and a value of exchange coupling, N, H, and J. I just put a comment that if N is greater than 12, lower N, because I don't want the code to run for like 1 hour, crash my laptop. So I just put this note that I'll not do N equal to greater than 12 at the moment. So the first thing I do is I build a two-site Hamiltonian. For example, a two-body Hamiltonian first, and that Hamiltonian is nothing but ZZ, right? So if there are two sites, there's Z1, Z2, and that is exactly what this is, so ZZ. And then I also build some objects which we'll need later on, which is HX. HX is poly at X multiplied by identity at site 2, and then identity at site 1 and poly at X site 2. And similarly for HZ, right? So this is what I have. But this is for two sites. If I have more than 3 sites, which is usually the case then I do a loop from 3 to n plus 1, and I construct the Hamiltonian in terms of this. So for example, I first take the 2-site multiplied by identity, right? So now it becomes a 3-site object. And then I permute that ZZ to the second and the third site and multiply by the identity on the first piece. And that gives me HZZ. This is just a trick to do exact diagonalization. When you have to do exact diagonalization, this is one of there are different ways of doing this, but you can build Hamiltonian like this by using loops. So you take 2, and so 1, 2, 3 is you take interaction on the first 2 sites and then identity on the third, and then flip it. And similarly for the HX and HZ, for example, right? And then once I have this loop, I add a periodic boundary condition where I connect the last site to the first site by doing this. I don't need to worry about that for the on-site terms because they have been taken care of already. And the Hamiltonian is just H is equal to minus J times HZZ. So HZZ is the ZZ at neighboring sites over all the n lattice sites. And then this is exactly the transverse field Hamiltonian I wrote 5 minutes ago, right? So then I just return H and I'll also return ZZ just to need. So let's look at this at 5 sites, for example. If I look at 5 sites and I can set magnetic field, let's set the magnetic field to be close to 1, where there is a quantum phase transition. I build the Hamiltonian, diagonalize the Hamiltonian, find the minimum eigenvalue of that Hamiltonian. And then I can also create eigenvectors. So for example, you can do that as well. But eigenvalues sorted, for example. So this is just, you can compute it, the smallest eigenvalue like this, taking a minimum. Or you can also do it like, you can compute the eigenvalues and eigenvectors, and then you can do a sorting, and then you can do the minimum one. And this is the exact result which we have from the elliptic functions. So I call a special elliptic E, and then pi by 2 times the argument which I wrote, right? So this will give me an exact, this will give me a normalized eigenvalue. So for example, let's run this. Hopefully it should run without errors. So it's initializing. Okay, so the ground state energy I get is minus 1.2944 something. The exact is 1.2732. And this is on how many sites? This is on 5 sites. So 2729. Let's go to 8 sites and run the same thing. Note that the computation time will become larger, but still can be done. So this is 2729 on 5 sites. And the ground state energy on 8 sites is 1.28. So we are almost getting closer. Ground state energy on 10 sites. It will take a little more time, and this is the largest N we'll run. So you can already see that we are agreeing to 2 digits of precision here. And the exact results is differing from the result from the elliptic function or the exact result at third decimal places, right? So this is a quick check of saying that, okay, maybe n equal to 10 is already taking it to 2 decimal places, but for some practical purposes, you might need a lot of precision. For example, you might need 10 digits of precision in your observable or energy, ground state energy, or some correlator you're computing. Or for people who do conformal bootstrap, they need like hundreds and hundreds digits of precision. So obviously we see that n has to be little large, it becomes harder. And that is why we want to not do exact diagonalization. So exact diagonalization is just like done for small systems to get an idea of what is happening. Okay, so is there any question related to this? This was the complete example of the ground state energy of transfer switch using model in 45 lines.
There is a.
Yeah. So is there any approximation here?
I cannot hear properly.
The question is whether there has been an approximation here.
Sorry, the question is?
Whether that
I'm not on there.
Yeah. Okay.
yeah, okay.
Has
Can
there
you,
been has there been any approximation here?
There's no approximation here. There's exact. I'm not.
why are you not getting, then why are you not getting exactly the exact answer?
Oh, so exact result is in the thermodynamic limit. I'm not in the thermodynamic limit.
Oh, I see, I see. So the correct answer is actually the top one. I mean, the exact one is not
Oh,
exact.
yeah. So, okay. So, yeah, maybe. So,
Yeah. Okay.
yeah, sorry. Let me just run it quickly. Yeah. So, yeah, what I'm computing is for some 10 sites, the exact result in thermodynamic limit is something else.
Okay. Any more? No, I think that's fine.
Okay, so this was a short example where we saw the agreement with the exact results. I could have done this for range of, for example, range of magnetic field and showed you a plot. I don't know, I had that somewhere, but I can't seem to find it right now. But yeah, you can do it. The building the Hamiltonian is important. You can just play around with different values of n, different values of h. We know the exact results. You can also, if you want to carry on from here, you can also compute the magnetization. So you compute the ground state and you can look at the magnetization. The magnetization will show you that around h equal to 1, there's a phase transition because the magnetization has the steepest slope at h equal to 1. So those things you can try. But this was a simple example just to show the exact diagonalization. So for example, even if when we are doing quantum computing, we try to take some Hamiltonian and do exact diagonalization to see how the quantum computers are performing, for example. So we recently studied this SYK model where we did the exact diagonalization for the SYK model, which is some complicated Hamiltonian system. And then you can do the same calculation using quantum computing and see whether you get the exact energy, whether you get exact things. So it's just like a good check. Okay, so if if that is done, I'll now try to go and do some tensor contractions uh, uh, examples so that we all are on the same page. For example, let me share the screen for that again, sorry. Okay, yeah. Yeah, so do you see the plot?
Yes.
Yeah, so this is what I wanted to show. This is not in the notebook because I don't know where it disappeared, but I just see it right now, so I'll just show you. So I was also playing around with different magnetic field, for example, H. This is on some 8 sites or something like that. I showed you an example, if you remember, for H equal to 1, but you can do the same thing for different values of magnetic field and compute the exact result is the theoretical result, and then the ED is the what we did. So you can do it for a range of magnetic fields and things like that, right? So this is what I wanted to show. So suddenly popped up. So now what we want to do is let's see. So
Can you hear me?
yes.
So, like, why is is it like in the plot you showed, why is the result so close to the theory result without taking the thermodynamic limit in the exact diagram?
Yeah, because when you switch off the magnetic field, then the ground state is basically trivial, all spin up. So the need of the thermodynamic limit is related to how complicated the ground state structure is, and it depends on the range, the parameter space you are in. So different parameter spaces have different convergence with the number of sites. The slowest convergence is often at the critical point because that is a phase transitions usually happen in the large number of degrees of freedom. So you really need large n. But the dependence we saw for h equal to 1 is not the dependence you see for h equal to 0.1. It might be different.
Thank you.
Yeah, this is a common point in like almost most of the models, toy models, and etc. That different points and all points in the phase space don't have the same thermodynamic limit in the sense that the scaling with the degrees of freedom is different. It depends on whether they are close to the phase transition, what kind of properties they have, and things like that. So yeah, for some you just don't even need to go beyond 10 probably for very small values as you saw. Okay. Now what I'll do is before we set and start doing tensor networks, I'll just show you very simple things which we'll need later on. So for that, I will do this and I'll construct some random matrix of say size 10 by 10 is good. And then I can copy this same thing, but rename it B. And then what we'll do is we'll do it 2 ways. The first is the usual matrix multiplication. So this at the rate sign in Python is used for matrix multiplication. So this A dot B is matrix multiplication. And the second way of doing this is what we are going to do now. So in tensor networks, there's a very useful NumPy routine, which is called Einstein summation convention. You can read more about it here. Evaluates the Einstein summation convention on the operands and other details. What it basically means is that you have to write something like ij comma jk going to ik and for a comma b, right? So this is a simple way of doing a matrix multiplication. This is more tensorial way of doing a matrix multiplication, right? They do the same thing. How do I check whether they do the same thing? I'll just print whether all the elements of out1 and out2 are close to each other. So that command is called np all close. If np all close is true, then the matrices are the same to the machine precision, I think 10 to the minus 14 or minus 15 or whatever. If they're not the same, then they are different. So let's do this small exercise. and run this cell here. So it's true, right? And that's true because this is matrix multiplication. This is now suppose I change it. For example, I have all the dimensions are the same, right? So I can uh, uh, let's see. So now the thing is, if I do even this, right? The Einsam is smart enough to not see, is not smart enough to see that these indices are all same and you can contract this to this. So this is false, right? Because it is now contracting these two things together. So the order has to be same here. For example, if I do ijjk, ik, it gives me the correct thing. And if I do something else, it's just not smart enough. So usually Einsam is the simplest way of doing this. What if we get some time today, I'll show you more fancy. So for example, if I am doing, say, yeah, let's go to that a little later. So this is simplest way, but often slow. So we don't use this in research papers or in practice when we want to do big calculations. So this is just to show you an example. Now, there's a way to make this fast, which is if I do something like optimize equal to true with a capital T, I think. Yes, I think this is okay. And it still does this, does it probably a little quicker, I think, compared to not optimized flag turned on. So this is a small check. Now, once we know this, let's do a more complicated check for not just two, but let's see. Now we have three tensors of rank 4, and we want to write some output, say out 3. And how do we want to write it? I want to write it like ijkl, jiqr, so jiqr, lkab gives rqba. And then I do B, sorry, A, B, and C. Right? So let's see, and then I can print the shape of the output tensor, and let's run this. So now it's contracting three rank 3 tensors and giving a rank, sorry, yeah, 3 rank 4 tensors and giving an output which is still a rank 4, right? So this is the contraction pattern it is. Now we can be a little picky, and what I'll do is, so this is the second index, right? And this is the first index on the second one. So I'll make this 5 and I'll make this 4, and let's see what happens. It gives me an error, right? Obviously it has to give me an error because I'm contracting the second index of the first tensor with the first index of the second tensor, and they don't have the same size. So Einsam is like, I cannot do it. Okay, so you have to, once we feed in the tensors, we have to make sure that we're contracting the tensors which have the same dimensionality and legs and so on. And those things are easy to keep track using by making diagrams and things like that, right? So for example, let's change this to 5. And then it's happy and it gives me a contraction and I get the same rank 3, right? So this is a simple example of tensor contraction. We'll be using a lot of these things in the next 20 minutes where I show you how to, if we reach that one, because I have to also talk about the theory of constructing those initial tensors. But yeah, we'll see a lot of these things later on. We'll even see a better optimized version of this. And we'll see, I'll try to also do these contractions once on CPU and once on GPU, because we wrote a paper last year where we showed that there's a factor of 10 and more if you use GPU for these kind of contractions, because these tensors here are very small. In practical meaningful calculations, these tensors are like 70, 70, 70, 70 or something, or maybe 100 times 4. And there are like 4 tensors, 6 tensors, each of them with 100 to the 4 elements. So it can get really messy, right? Are there any questions at this point? I can also chat this, put in the chat. Sorry, I didn't do that. I'll do that now. Chat. Okay. So if there are no more questions, then I want to go back and talk about the course training, basically. So we know what tensors are, how do we contract them? Now we want to go back to the Euclidean action, or we want to write down some model and then write the tensor network representation of that, and then try to coarse grain that tensor. So start from one tensor and then combine 4 tensors to get a new tensor, then combine 4 of those new tensors. So I'll show you one step of that coarse graining, real space coarse graining, and then we'll come back to Google Colab and do some coding. Okay, so let me go back to iPad. Okay, so we saw that this was correct. We checked this result, but now we go to the so want to talk about the classical easing model, which still have for which z the partition function is known exactly, or the log of the partition function and its derivative is known exactly. So one of the first things we do in any tensor network computation basically is to look at the Boltzmann weight. Right? So for example, e to the minus b si sj plus. So there's a square lattice like this, say 2 by 2. You go to the dual lattice, and then you have 4 links like this. So you have to make a tensor of rank 4. And how do we make a tensor of rank 4? We have to find one of these things, and then we have to multiply 4 of these legs. So we have to make a matrix basically, because this is Z2 symmetric model. So we have to make a matrix. And then once we have the matrix, then probably what we can do is we can, sorry. Right? Now this matrix here, so we eventually want to get to a rank 4 tensor T, which describes which is like the tensor for the classical easing model. And we have to get here. So we can get here by noting that this is like this. So if this index is I, this is A, but these are contracted. So you're left with the free ones are the IJKL. So we want IJKL, but all of these have 2 indices. It's a matrix, 2 ends. So we find 4 Ws and then contract them in certain manner. And the way we constructed this W is based on the Boltzmann weight, right? So using the Boltzmann weight, whether the spins are the same, whether the spins are different, we do that. And you'll see an example when you start to code this up. So suppose we have this example, and note that this tensor will depend on beta, as it should, because this Boltzmann weight is the e to the minus b, this thing, and this thing here is going to contribute to Wij, for example, sorry, Ia. And all these are the same, right? So it's the same matrix, but you have to, so it's like a same matrix and you have to multiply them in certain manner, contract them in certain manner, right? Because this is equivalent to this is symmetric. So there's nothing which differentiates it. This is just like nearest neighbor interactions. That is why there's Si, Sj. So once this weight, I'll show you how to go from this weight to the matrix decomposition. And this can be done for easing model, which is Z2 symmetric, or it can be done for a POTS model, which is Q symmetric, or it can be done for XY model, which has a O1 symmetry. It can be done for SU2 gauge group. So we have done all these cases. So these are all, so this we did in 2019, this we did in 2020, this 22. So all these cases can be expanded like this and you can study them, right? But for now, I think I'll consider this case, and then I'll also show you that how does it extend when you have a ZQ symmetry, for example, right? So ZQ symmetry is nothing but the generalization of the Ising model. So Ising model, you can have spin up and spin down. So you can think of not North Pole and South Pole, but at 120 degrees of angle over a circle. And that's Z3 symmetry. And similarly, you can take 4 points, 5 points, and so on. In the limit of n going to infinity, it goes to this continuous group, which is the U1 group, right? So all of these models have been studied using tensor network methods. Okay. So once we have this tensor, for example, suppose we are in 2D all along. Once we have this tensor, what do we do? The TRG procedure says that you combine two of them and do some sort of coarse graining. But what we will be focusing on is called the higher order TRG, where you take more tensors and do a better decomposition of that. So we will not do this, but what we'll do is directly higher order TRG. By the way, I just want to point out that there's a very nice website by Glenn Lee, who was a postdoc at PI and now is at Amazon. He has a very nice website, which, sorry, it's called Tensors Net or something. Let me see. So there are a lot of code there. So you can go and find any code you want, basically. Right. So if you just, I don't remember. Yeah, it's either tensor.org or tensor.net or something, but it's by Glenn Evenly. So there are DMRG code, MPS codes, TRG codes, Mera codes. So everything is online, and they do a lot of different models: Heisenberg model, transverse field Ising model, and there are a lot of other resources. So, for example, if you want to get started, there are like many websites properly dedicated to tensor network studies. There's iTensor, then there is Tensor, 10Pi. This is in C++, this is in Python. And there are a lot of reviews which you can find online. I have not given them, I have not given those. Yes, that's right. I think this is tensors.net, right? Yes, so this is tensors. I have not given those because it's easily available online. It's not like. So yes, you can always check those, and you can always have codes from there. Just a second. Okay, so now what we want to do is, once we have this tensor, we want to contract it. So for example, I have a tensor like this. Now, this is what we start with. So this can be represented as, say, A0. Zeroth step of coarse graining. I've not done anything. I've just written down the initial tensor in terms of Boltzmann weight. Now, just to make a point, this idea of tensor renormalization group goes back to the early days of spin blocking, if you're familiar with that. So in 60s and 70s, Wilson and Kadanoff started thinking about renormalization group, and they started thinking about spin blocking methods. That was one of the earliest ways of doing RG transformation. So let me just quickly say a few words about that. So for example, suppose you have a very big, so suppose you have an 8x8 lattice, right? And there is spin lying on each lattice side. What they said was, you can reduce this 8x8, for example, you can coarse grain the system, you can reduce it to something like 4x4 or bigger parts, where if the spin is up, down, up, up, you take the average. So this is 3 ups and 1 down. So you replace it by up, right? And this is first step of coarse graining. And you do the similar thing for other things. And then you combine more blocks together. And eventually you reach some level after doing some steps of coarse graining. You reach a limit where you have the effective description of what you started off with, but with less degrees of freedom, which is easier to handle. But you have to adjust your couplings when you go from levels, or you have to adjust or manipulate such that the partition function remains the same, or you can keep it same. So this is the basic idea of these blocking, exact blocking developed in 60s and 70s. What we are doing right now is not representing, we are saying that we will represent these objects or the smaller objects by tensors, and then combine these tensors together. And tensors have the information about the Boltzmann weight. So we are not dealing directly at the spin level, but we are making a combination, higher dimensional combination from the spins, and then coarse graining it. And it turns out this is a better way of doing a renormalization group, numerical RG, for example, because of the results we see and the accuracy it has. Obviously, this also has some limitations, but the basic idea goes back to the 60s, but it's now more sharp in the sense that you can get better approximation. So suppose we have this tensor. The first step is to combine 4 of them together. So 4 of them together, how do we combine 4 of them together? Now this has 2 to the 4 elements for Ising model, right? Because each of the leg is either corresponding to a spin, 2 spins plus 1 minus 1. This is a classical spin. And this has 2 to the 4 elements. This can also be seen because each of these are 2 by 2 matrices. The same 2 by 2 matrices, and this has 2 to the 4 elements. So once we have one tensor, initial tensor, then the first step of coarse graining is related to the fact that we combine 4 of these tensors together. And how do we combine them? We combine them in a certain manner. So if we were not doing coarse graining, if we are just not doing coarse graining, we are just at fundamental tensor A0, and we want to build a scalar out of that, we build it like this. So this can be Z, but this is not Z because it's like initial tensor. Usually you have to start with some tensor, you have to coarse grain, and then you have to throw away the singular values in the singular value decomposition. But once we reach from here, we reach AN, then we combine 4 of these ANs to make this Z. So this is an approximation of Z because all the indices are contracted over, and this will give you a partition function approximation, right? But for the first step, that is not what we want to do. So we want to just keep these tensors and do singular value decomposition out of that. And for that, the way we do it is we combine these two, we combine these two, we combine these two, we combine these two, combine these two, we combine these two. But we leave this index, this index, this index, and this index free. So there are 4 indices which are free. I have not contracted over them. And with 2 indices on the left, 2 indices on the right, I make a matrix out of this. How do I make a matrix out of 4 rank object? It's very simple. You just fuse both of these legs together, fuse both of these legs together. It's a matrix. Once we have the matrix, then we do a SVD of that. Singular value decomposition, right? SVD of the matrix will give me something which will have some number of singular values. If the singular values cross some number, if the number of singular values is greater than D, then I truncate. If number of singular values is less than D, no truncation. So it turns out, we'll see that maybe clearly tomorrow. It turns out for the Ising model, the first 3 steps of coarse graining can be done exactly. You don't need to truncate. And that's good because easy model is supposed to be simple, right? Because there's just 2 to the 4 elements, less tensor size is less. So we can do, I think, 3 or 4 steps of coarse graining exactly. But once we go beyond 5th step, you have to truncate. And note that the size of the tensor is growing at each step. And we'll come back to that question a little later. So make a matrix, do a SVD, truncate the SVD based on this fact, right? And then what do you do? So suppose you have from SVD, you remember if we the lecture from yesterday that SVD gives you U, S, and V. It gives you 3 matrices, U, S, and V. U and V, people also call sometimes in tensor network language as projectors or isometries. So with this USB from the SVD of this matrix, I fuse the initial tensor, which is rank 4, using this U. So how do we use this U? So this is U. So now note that this U is can be decomposed into a rank 3 object. So this U, we'll see that tomorrow in the code explicitly, that U is a rank 3 object. It can be, so once we do the matrix from the rank 4 objects, you can decompose this U into rank 3 object, this into some other matrix object, and this into again rank 3. And this is U, and this is U. And this is the initial tensor, which is A0. And this is the initial tensor A0, right? So, and these dots are the indices which are contracted over. So I contract this leg with this leg with this leg with this leg with this. Note that now we still have 4 free legs. First, second, third, and fourth. Now this constitutes one step of coarse graining along a particular direction. So I'm taking the tensors aligned in the vertical direction right now, right? Now there's another procedure. So once we have this tensor, you do
Sorry.
the
Yeah. The middle index, right?
Oh yeah, sorry, yeah, that's just right. Yeah, I missed that. And also on this one. No, not on that one. Yes, this is 4 legs. Right. So suppose now this gives me a tensor which is a green blob, which is T twiddle, right? So now we take this T twiddle, for example, let's take this T twiddle. Yeah, one of the things about tensors is that at least you have to draw a lot of diagrams initially. It's like diagrams really help because there are a lot of indices. So for example, this is one half part of one coarse graining, and the second part will come to now. So once we have this tensor, we now combine 4 of these tensors, just like we did with the other one, right? But now we are not going to leave these 4 legs, right? But we are going to leave the 4 legs on the other side. So leave this, and this. So that means contract these 2, 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 contract these 2. Right? So now we have, initially, when we're doing along one direction, we had to take the decomposition on the, leave the indices on this side. Now we leave the indices on this side, and we construct the same projector, but now the projector will be on the top, and we can construct the tensors like this, and then we can construct a projector like this. And these are the free indices. Right? It's exactly like rotation, basically. You do it along one. At the end of this tensor, what we find is we get A1. We started with A0, do all this thing, we get A1. And this is one step of tensor coarse graining using higher order TRG. It's simpler in the case of TRG, but we are using higher order, so it's a little messy because there are more tensors. But yeah, it's not very difficult to understand. We'll write a code starting tomorrow, where we'll build this tensor for the easing model, and then we'll construct these U and V's, and then we'll do this step, we'll do this step and reach this step. So this has to be one loop, right? You give it an input is this, output is this. The operations are, these are the operations. And you just have to write this once. You write it once, a function which does all this, and then you keep changing the input. So now this becomes the input for the second step, and so on. And if you do this coarse graining n number of times, here we have done this just once. So basically you go from something like this to go from something which is the description on something like this. So you go from 1 by 1 to 2 by 2. If you take this tensor and combine 4 of them together, you go from 2 by 2 lattice to a 4 by 4 lattice. So if you keep on doing this, truncating the singular values from the SVD sufficiently so that it fits in the memory, everything is fine, and you do this n number of times, you get at a tensor which is a to the n, and then you can build a partition function out of that, which we just saw here. Contract everything, don't leave any legs, and that z is the partition function of the system on a lattice of size 2 to the n times 2 to the n. And that is an approximation of the actual partition function of the classical statistical system in the thermodynamic limit. It's thermodynamic limit because we'll see that n is equal to 30. So it's a huge lattice. The only constraint is that we have to truncate some eigenvalues of the singular, basically truncate the singular values in the SVD. And that is going to bring us some error. But I'll show you that for easing model, when we do this, the accuracy compared to, say, Onsager's solution is 10 to the minus 8, 10 to the minus 9 tomorrow. So these things really work in practice. Like you can reproduce Onsager's result to 10 to the minus 8 in 30 seconds, basically, right? In the thermodynamic limit. So that is why this is such a powerful method. So similar to the MPS methods for the quantum spin chain, this is the classical approach to the field theory and spin models. So we'll continue there, I think, tomorrow. And then we'll start by defining this tensor and then doing this coarse graining and showing you the comparison of the Onsager solution for h equal to 0. We can also do h equal to non-zero for easing model. The exact solution is not known, but we can, tensor doesn't care about whether h is 0, h is not 0. The procedure is the same, everything is same. So we'll also do it for h non-zero and then continue from there. Yeah, thank you.
Thanks. Last question. So to make sure your A1, how many components does it have? Is it 2 to the 4 or 4 to the 4?
It's 4 to the 4. It's 4 to the 4.
Yes. So each line there now can take 4 values.
That's right. It's now 4 to the 4th. Sorry. And now the next step will reach 8 to the 4th, and then we'll reach 16 to the 4th. So I think that's still manageable. So that is why this is all exact. And once we start going beyond 16 to the 4th, maybe we'll do 64 to the 4th as well. But this thing is problematic, so we have to start truncating after 1 step, 2 step, 3 step, 4 step. After 4 steps, we have to start truncating starts here. This can be easily written in code, like we don't need to care about it. It will automatically truncate if it is exceeding some size. We just need to know the biggest size we can deal with. And for example, it's 70 to the 4th, 80 to the 4th, depending on what machine you are in. So we have gone till 100 to the fourth. So we don't truncate anything if the size of the tensor is less than 100 to the fourth. But if it exceeds that, we have to truncate.
But it's not that you're truncating the size of the tensor, you're truncating inside the tensor, like you're simplifying
Yes.
components of the tensor.
Yeah. So we truncate at this stage where we have this use. Because use the singular values you can attach singular values here. The diagonal elements is just a number, scalar number. So we truncate in these u's, how big these u's are. And that eventually determines the size of the tensor you are ending up with. Yeah, we'll see this in working in practice tomorrow, I guess.